Hello everyone and welcome back to this series on the STM32G4 and real-time signal processing. The topic of this video will be the ADC. Specifically, I will demonstrate how to use ADC polling, DMA continuous conversion, and DMA timer triggered conversion. Every chip is a little different, but on my chip, the STM32G491RE, there are 3 individual ADC modules fed from up to 36 different input channels. The ADCs have a native 12-bit resolution, which can be increased through oversampling up to 16 bits. Most importantly, the ADCs can reach speeds as high as 4 megasamples per second at the native 12-bit resolution. It is possible to increase the sampling speed to even higher numbers by dropping the resolution to 10, 8, or even 6 bits. As an example, if one were to reduce the resolution to 6 bits, a sampling speed of over 6.5 megasamples per second is possible. However, it is important to note that not all of the channels can reach the 12-bit 4 megasample per second speeds. Only the fast channels, channels 1 through 5 on ADC 1 and 2, are rated for this. All other channels are considered slow channels and max out at 2 megasamples per second. With 24 different input channels, there are a lot of pins to choose from. For this video, I will be driving pin PC3. This corresponds to channel 9 on ADC 1. I'm doing this simply because of the ease of access that this pin has being on the bottom left-hand corner of the board. Notably, being on channel 9, it is a slow channel and thus not capable of reaching 4 megasamples per second. Jumping right into it, the first of the 3 examples will cover software polling. Essentially, this is just manually telling the ADC each time we wish an analog to digital conversion to take place. It is the easiest way to operate an ADC, and it is the traditional way to use them on a microcontroller. We ask the ADC to read the analog pin, and it will return 1 digital value. By default, the ADC within the cube IDE is configured for software polling. Therefore, the only hardware changes required is to enable the ADC, ADC1, and configure input 9 to in9 single-ended. ADC polling requires 3 lines of code to be run for each analog to digital conversion. The first line of code, HAL ADC start, turns the ADC on and instructs it to perform 1 conversion. The next line of code, HAL ADC poll for conversion, will halt the processor until the ADC has finished. If this command is absent, we risk reading the previously sampled value from the ADC or receiving corrupted data. The last line, HAL ADC get value, is how we will read the value of the ADC and store it in memory. Finally, the exact decimal voltage of the analog signal can be acquired by multiplying the ADC value by the reference voltage and then dividing by the max ADC integer value. For all STM32s, the reference voltage is the operating voltage, which is 3.3 volts, and 12 bits corresponds to 4095. I will now open the Cube IDE, create a new project, and initialize all peripherals within their default mode. Starting within the IOC file, I'll first navigate to Analog, ADC1, and set in9 to in9 single-ended. Next, I'll make sure that my desired pin, PC3, is enabled and is set to ADC1 in9. Now, with the ADC enabled, I can generate code and switch to the C perspective. Within the main.c file, I'll begin by creating 2 variables within the user code private variables section. The first is an integer to store the ADC's value. The second is a float to store the decimal value in volts. Next, within the user code 2 section, I'll create a scalar used for converting the integer returned from the ADC to a decimal voltage value. Now, within the user code 3 section, I will add the code to run the ADC. The first 4 lines are the ADC polling code we just saw that perform one conversion and convert the returned integer to a decimal voltage. The last two lines toggle the LED each time the ADC is read and provide a 1 second delay between ADC samples. Now, I will plug in my STM32, turn on my voltage source, build the code, and switch to the debug perspective. Within the debug perspective, I'll navigate to the Live Expressions tab in the top right of the window. Here, I'll add my two expressions that I want to watch. The integer ADC value and the value in volts. Finally, I'll click Resume. As we can see, our two expressions are now constantly updating as the ADC performs its conversions. Now that we are able to perform ADC software polling, let's evaluate the maximum sample speed that this method of operation supports. I will do this by measuring the execution time required to obtain one sample. As demonstrated in the previous video, I'll use timer 6 and set the tick rate to 1 MHz through the use of a prescaler. Additionally, I'll leave the counter value at its max value of 65,500. Thus, we will count the time it takes in microseconds for the conversion to take place, with a max counting time of 65 milliseconds. Therefore, the only hardware changes required is to enable timer 6 and set the prescaler to 170-1. As seen in the previous video, measuring execution time requires only 3 lines of code: 1 line to start the timer, 1 line to reset the timer, and 1 line to read the value of the timer. Returning back to the Cube IDE, I will first navigate back to the IOC file. Here, I will activate timer 6 and set the prescaler to 170-1. Next, I will regenerate code and transition back to the C perspective. Starting from the top, within the user code private variables section, I will add an unsigned integer to store the value of the timer. Next, within the user code 2 section, I will add the code to start timer 6. Finally, I will place the code to reset the counter before the ADC runs, and then to read the counter's value afterward. Now, I can rebuild the code and return to the debug perspective. I will now add the timer value variable to the live expressions and resume the debug. With debug running, we can now see that it takes 6 microseconds to perform one conversion with the ADC. With the execution time measured, the max sample rate can be calculated using the formula on screen. For this case, a 6 microsecond conversion time correlates to roughly 170 kilosamples per second, which doesn't sound too bad, but once you consider that this is the max sampling speed with the processor unable to perform any other operations, it's really not good. When performing polling, the CPU has to spend clock cycles waiting for the ADC to complete its current conversion, then to read the data registers and transfer the data to memory. As we just saw, this consumes considerable CPU resources and bogs down the processor. Fortunately, we can use direct memory access, or DMA, to offload the processor's task to the DMA controller and let our peripheral, the ADC, run independently in the background. The DMA controller now adds a new route for data to traverse to reach memory, allowing data to travel between peripherals without passing through the processor. Thus, instead of the CPU waiting for an ADC conversion to finish, then reading the data register to memory, the DMA controller will automatically transfer the data to memory each time a conversion is completed, circumventing the CPU. Specifically, the DMA controller will store the ADC data within a reciprocal buffer we allocate in software. To run the ADC in the DMA configuration, a few extra parameters must be set within the IOC file. Like before, the ADC ADC1 in 9 must be activated and set to single-ended. Next, within the ADC parameter settings, continuous conversion mode and DMA continuous request must be enabled. These two lines instruct the ADC to continuously run after it starts and allows the DMA controller to continuously stream the data to memory. Lastly, ADC1 must be added to DMA. Then, within the DMA settings, ADC's 1 mode must be set to circular and the memory data width to word. The circular mode allows the DMA controller to wrap around to the start of the data buffer when it is filled. Lastly, setting the memory data width to word allows us to directly store the ADC data in an array of 32-bit integers. In the default half-word state, the ADC data is configured to be stored in a 16-bit integer. Storing that data in a 32-bit integer will cause it to be left shifted by 16, forcing us to do some extra work within the software each time we wish to read a value. The code required to run the ADC with DMA is incredibly simple, as it only requires 3 functions to get the ADC up and running. The first is HAL ADC start DMA, which, as you could probably guess, will start the ADC in the DMA configuration. Additionally, this function requires us to pass in an unsigned 32-bit buffer and its length. This is the buffer. Within the Cube IDE, I will now create a new project for DMA and initialize all peripherals within their default mode. Beginning with the IOC file, I will first navigate to ADC1 and set channel 9 to single-ended. Next, I will select DMA settings and add ADC1, then set the mode to circular and the memory data width to word. Now, I will return to the parameter settings and enable continuous conversion mode and DMA continuous requests. Finally, I can now generate code and transition to the C perspective. Starting from the top of the newly generated main.c file, I will first set the buffer size within the user code private definition section. Next, within the private variables section, I will create the ADC buffer and another variable that will be read as an example. Next, within the user code 2 section, I will place the code to start the ADC with DMA. Finally, at the bottom of the file, within the user code 4 section, I will place the 2 callback functions. Notice that I've placed the ADC value variable within the conversion half complete callback function. Thus, the value will update each time the first half of the buffer is filled. We could just as easily place code within this callback to operate on the rest of the values within the first half of the buffer if desired. Now, I will build the project and switch to the debug perspective. I will now add the ADC value variable to the live expressions and select Resume. It can now be observed that the ADC is running and the ADC value variable is constantly being updated. Now that the ADC has successfully ran with DMA, we can evaluate the sampling rate improvement obtained compared to polling. Again, I will make use of timer 6 and set the prescaler to 170-1 to count in 1 microsecond steps. In addition to reusing timer 6, the same 3 lines of code can be recycled from the previous example. First, HAL time base start will be called to begin counting on timer 6. Then, within the conversion half complete callback, the counter will be reset to 0. Lastly, within the conversion complete callback, the value of the timer will be read. As configured in the example, the ADC buffer has a length of 5,000. Therefore, when this code runs, the time required to fill half the buffer, or 2,500 samples, will be measured. Like before, back within the cube IDE, I will navigate to the IOC file. Now, I will activate timer 6 and set the prescaler to 170-1. Now, I will regenerate code and transition back to the C perspective. Starting from the top, within the user code private variable section, I will add an unsigned integer to store the value of the timer. Next, within the user code 2 section, I will add the code to start timer 6. Finally, I will place the code to reset the counter in the half complete callback and then to read the value of the counter within the complete callback function. Now, I will rebuild the code and return to the debug perspective. Fortunately, I still have the timer value variable from the last demo within the Live Expressions tab. Therefore, all I need to do now is resume debug. We can now observe that it takes 883 microseconds for the DMA controller to fill half of the ADC buffer. Now that the time required to capture 2,500 samples has been measured, the sampling rate can be calculated. Using the formula on screen, we can see that the ADC was sampling at roughly 2.8 megasamples per second, nearly 15 times the speed of software polling, with, however, the advantage of no processor usage. While DMA continuous requests offered a sizable improvement in sampling speed, it comes with the drawback that the exact sample rate cannot be specified. Therefore, the third and final example will demonstrate how we can use timers to drive the ADC at precise sampling speeds. Specifically, we can configure a timer to generate a trigger event each time the counting period has elapsed. This trigger can then be fed into the ADC to start a conversion. By selecting specific prescaler and counter period values, the sampling speed of the ADC can be set. For this example, I will run the ADC at precisely 1 megasamples per second. I will accomplish this by using timer 7, setting the prescaler to 17-1 and the clock period to 10-1. Thus, the counter will tick with a frequency of 10 MHz and reset every 10 ticks, thus creating an output trigger of 1 MHz. Therefore, our new timing system will look like this. The hardware setup for this example will be similar to the previous. However, this time, continuous conversion mode will be disabled, and the external trigger conversion source will be set to the timer 7 trigger out event within the ADC parameter settings. Additionally, the DMA settings will remain the same, but timer 7 must be activated. Again, I will be setting the prescaler to 17-1, the period to 10-1, and the trigger event selection to update event. Finally, we can reuse the same code from our previous DMA example. Specifically, HAL ADC start DMA and the 2 callback functions. What's new, however, is a line of code must be added to start timer 7, Without starting the timer, the ADC will not be triggered. For the last time within the Cube IDE, I will create a new project and initialize all peripherals as default. Beginning within the IOC file, I will first navigate to ADC1 and set channel 9 to single-ended. Next, I will go to the DMA settings, add ADC1, set the mode to circular, and the memory data width to word. Now, I will return to the parameter settings and enable DMA continuous requests. This time, the continuous conversion mode will be left disabled, but the external trigger conversion source will be set to timer 7 trigger out event. Next, I will activate timer 7, set the prescaler to 17-1, the period to 10-1, and the trigger event selection to update event. Now, I will save, generate code, and transition to the C perspective. Again, starting from the top of the newly generated main.c file, I will first go to the user code private definition section and set the buffer size. Next, within the private variable section, I will again create the ADC buffer and add another variable to be read as an example. Now, within the user code 2 section, I will place the code to start the ADC and to start timer 7. Finally, at the bottom, within the user code 4 section, I will place the 2 callback functions. Now, I will build the project and switch to the debug perspective. With the ADC value variable still being left over from the previous example, all I need to do now is select Resume. We can now observe that the ADC is running and the ADC value variable is constantly being updated. And that's it. Thanks for watching and stay tuned for the next video, where I will introduce the DAC and tie the ADC and DAC together to create our first signal processing system. Thank you.